Now, binomial distributions had a certain number of trials, and those trials had certain values that could be included and certain values that couldn't be continued. That would be considered discrete data. But when you have continuous data where everything is allowed, and it happens to cluster around the average or the central value or the mean, it makes a nice bell curve, and it's called a normal distribution. We have two parameters, the mean and the variance. And if you have the variance, you can always square root it to find the standard deviation. And so we write the notation very similar to the binomial distributions notation. Binomial distribution, you had number of trials and probability of success. And now here, we write down what the average is and what the variance is. So this is notation stuff. And I already showed you last class the 68, 95, 99.7 rule, which if you draw out your bell curve, roughly 68% is between one standard deviation above and below. It's actually a little bit more. It's not exactly 68, it's like 68.2, but 68.2 sounds not very good in the rule, so we tone it down a bit and just said 68. This would be easier to remember. Same thing, the 95 is not perfect, but it's close, so we use 95. And then we couldn't just say 100, because that would mean everything was possible. We have to leave the possibility for things to be out there beyond, but it's very small. So that's why we have 99.7. These are not exact values. These are just estimates. We're going to find out how to use a calculator to have them exact. And this is in probability, but it's really a key thing in statistics. So this is where probability and statistics come together. So if you were studying statistics in university, you definitely would be studying normal distributions, because they tell us a lot about things that happen in real life. Okay? People's heights follow this. A lot of people are around an average height. Then as you go further away, there's less and less super tall people and less super short people. Weights do this. We all are around an average weight. But there are some people that are super skinny and some people that are not super skinny as a result. And the data seems to fall around here. Now, if you're in marketing or if you're in sales and you're retail, this is important data. Because you're not going to order for the new shirt that you're trying to sell. You're not going to order 10 extra smalls, 10 mediums, 10 larges, and 10 extra larges. Because you're going to be sold out of the ones in the middle and be stuck with extras on the ones that are really big or really small. So you have to take in these statistics to figure out things. Okay. So, almost all the values are within 3 standard deviations above and 3 standard deviations below. We got the 68, 95, 99.7 rule. Oops. And there is the normal distribution uses the mean and then 1 standard deviation, 2 standard deviations, and 3 standard deviations above. Then there's something called the standard normal, where you just call the mean 0, 1 standard deviation above 1, 2 standard deviations above 2, and 3 standard deviations above 3. And then it's more of a way of comparing. And this is what we're going to do with these tests. Right? let's say I decide I am going to give a pencil to the top student in the class. And on this side, you know, this excitement is growing. You can't wait to get this guy. This side, the top student got 11 right out of 25. And on this side, the top student got 8 out of 20. So if we just did the math, this one would be almost a pass. 44%. And this one would be 40%. So we did the math. The 44% should get the pencil, the prize pencil. I might even etch my initials in it like a signed pencil. I know now. Now you're like, I hope I win. Okay, this is gonna be good. I'm gonna do it. The skip, yeah, JR, right in front of it. It's gonna be good luck for your tests. Okay? But all of a sudden, this side of the class starts to complain. Why are you complaining? Your test, was it easier or harder than this? Did you say yours was harder? Right? You had 5 choices to pick from. They only had 3. What if I gave another group multiple choice? 1 choice. Just choose A the whole time. How are they going to do? Probably pretty good. Right? Unless they get stuck on something. Okay? So now we have to come up with a way of deciding which is better. Is this 40% better or is this 44% better? And the way that we're going to determine that is by looking at our standard normal distribution and say the 11 is above average. How much above average? Maybe it's 1.2 standard deviations above average. But the 8 is 1.7 standard deviations above average. Therefore, the 8 should win the prize pencil, as opposed to the higher score. And this is done all the time because they have standardized tests that you have to write. Some of the American universities you want to get into, you have to write a standardized test. But the test this year is different than the test last year. And maybe someone wrote the test last year, but now is applying for university, and they're trying to decide who do they give the scholarship to, or who do they accept into the university. They wrote 2 different tests that had different averages and different standard deviations. What if one test was easier? That's not fair. What if one test was harder? That's not fair. So who do we decide gets in? Well, based on the average and how much above average or below average, they use these as ways of determining who's going to get a scholarship and who's not. Okay, yeah, so here is the standard normal one with the 0, 1, 2, 3, and we call how many standard deviations above or below you are your z-score. So if you were 1.5 standard deviations above, your z-score would be 1.5. And it's telling you how much above or below the average you are. Again, it's a normal distribution, but now your average is 0 and your variance is 1. Do you need to know this formula? No. But this is the actual function that draws that curve. It is a function. I don't think you even have this in your notes, right? So it's just, don't write it down. It's just interesting that if you wanted to graph this bell is determined by its mean, its standard deviations, and what value you put in for x. This is the formula for it. Isn't that a wonderful looking formula? Do you need to know? No. It's just interesting. And for normal distributions, the mean, the median, and the mode are all the same. And what's also fascinating about normal distributions, maybe I had it in here, did I? Yeah, the total area under the curve is 1. And that area under the curve of 1 represents 100%. It represents probabilities. So if I ask myself, how many people would I expect to be 2 standard deviations above in the test that we just did? I could use the 68, 95, 99.7 rule and say, well, I know that this from here to here is roughly 95%, which leaves 2.5% there and 2.5% there. So how many people got above 2? 2.5% should get above 2 on that quiz, which of this class, 2.5% would be barely one person. Probably nobody got over 2 standard deviations above. No, there are no retests. You know, that's going to be on the, happens every year, I hand it back, everybody's failed. Somebody says, have a retest. No, no retesting. Oh, please make sure that the people that aren't here come in and do the test. It's important that they get their results as well. So I just talked about this, that the area under the curve represents probability. And we have a way of figuring out the area under a curve with our calculator. Just right where we found the binom CDF and binom PDF, we use the normal CDF where we put in a lower value, an upper value, mean and standard deviation to figure out things. Did we have a question that we didn't finish last class? I feel like yeah. And you guys are just going to be nice and let me keep going. Do we want to finish that one? It was, we did, oh yeah, it was a Planck's one. Binomial distribution. Let's finish it off and then we'll get into our, we did this one though. Or did we not finish this one? We finished this one? Was there one we didn't finish? Yeah. This, and we had done that and not the rest. Good. Because I know some of you, it would really bother you if that was left blank after the fact, right? So for your health, we have to make sure we do these. Okay. We've got 50 trials. How do we find the mean of a binomial distribution? We take the 50, we multiply it by the probability. 50 times 2/7, we would expect roughly 14.3 times that you would get a blue mark. This doesn't take long to finish this question. The standard deviation, do you remember that we have on our formula sheet, we have that the variance is n times p times q. So that would be 50 times 2/7 times 5/7. And then the standard deviation will be 3.19. If you ever want to play around with, let's see if I can find it, binomial distributions on your calculator, you can hit the apps button and see if you have the app that's called, wait for it. Oh, there it was. They have a probability simulator in it. So you can decide, if you don't have any money, you can hypothetically toss coins on here. You can hypothetically, I want to roll some dice. Very fun. Let's see. I want, 2 dice. 2 dice, 6-sided, we'll go with 6-sided. Update after, okay. What happens? Let's look at this. And we can graph a frequency. Let's go back to okay. Here we go. Yeah, okay, sure, let's clear everything. Okay, let's roll. Let's hit the right button. We got a 12. That's super lucky, because that's highly unlikely. And so, from this data, we can conclude that the most likely thing you'll ever roll is a 12. This is not good statistics. But if we do this 50 more times, oh, I hit 50 more times, 50 more times, 50 more times, and we keep doing this, and this is why this is fun to play with, because if I got you to do this in class and keep data, how long do you think it would take you to roll 1,051 times, collect your data, and then put it into a histogram? It would probably take us a long time. Fascinating. What shape is our histogram turning into? A bell curve. A bell curve with 7 as the most likely, which would be your average. A bell curve which we could figure out our mean and our standard deviation and everything about it. Very cool. Does it happen with other things? Escape. Let's roll. No, oh shoot, hit the wrong buttons again. 20-sided dice. Rolling it 3 times. Oh my goodness. Yes. That's, oh. Yes. Yes. Roll it once. Oh, I only took 1. Oh, I hit the wrong buttons again. There they are. There they are. Oh, this is a bad example. But let's do it 50 times. What could I roll up to? 60. So I'm going to go to my window. Oh, it probably doesn't let me do that. Use your imagination. This would do this. And make a bell curve. That was a bad example. Anyways, so our binomial distributions, we're going to find out, will turn into normal distributions. But now we are going to turn back to where we were, which was, well, here we go. And a lot of things in biology are normally distributed. So chest measurements of 18-year-old males have a mean of 95 centimeters and a standard deviation of 8 centimeters. If the data has a normal distribution, we can now figure out what are the chances that an 18-year-old male has a chest measurement between 87 and 103. So the first thing I find very useful to do is to draw out a little bell curve, put the mean in the middle, and label 3 standard deviations above and 3 standard deviations below. Then 87 to 103 would be from here to here. And I like to use a crayon, so you might want to bring crayons to class to shade that in. Now we should be able to estimate this pretty good using our 68, 95, 99.7. What percentage do you think that should be? One standard deviation above and below. It was perfect, right? So according to the 68, 95, 99.7 rule, we would estimate this to be 68%. Now, if we want to find it exactly, we have to go to our calculator. And on our calculator, we go second distributions, maybe not, maybe I have to escape. Escape, yes, quit, yeah, I'm sure. Okay. Second, distributions, and it's right at the top, normal CDF. We have to do cumulative because we're adding up everything in between two values. So if you have the newer version, it says, what would you like your lower value to be? Our lower value is 87. Our upper value is 103. Our mean was 95 with a standard deviation of 8. If you don't have the newer version, you have to write it in with commas, and you have to remember what goes where. So more studying involved with the TI-83. If you have a TI-84 and this is not showing up, you can connect to another TI-84 and just update your operating system so it does. When you push enter, we said it should be close to 68%. It is 68.26. So rounded to 3 sig figs, 68.3%. Or as a decimal, 0.683. So our 68, 95, 99.7 rule, we find out is a little bit off. But for statistical purposes, close enough. Okay, wait for this. I'm gonna, sorry, just temporarily low. Oh no! That's not what I wanted. So bad. Never mind. I have an idea. There we go. Oh, yes. Okay. Oh. Don't worry. This will work out. Oh. Very nice. Oh, I drew it again. And now on this one, it says, what is the probability an 8-year-old has less than 87? So if we drew it on here, took out our crayon. If you have never colored in with a crayon on smartboard before, if you need something to de-stress, like, I'm telling you, it is as enjoyable as it looks. It is very, very fun. So now, could you use your 68, 95, 99.7 rule to estimate this? Now, at your 95, your 68 here would leave you with 32 on either side, right? So can you see that a good estimation for this one would be 16%, because you have only half of it. So that would be a way you could use the 68, 95, 99.7. But we're going to go to our calculator here, and this time, second distribution, normal CDF number 2, we need our upper one to be 87, and we need our lower one to be forever, infinity. Okay? Now, couple of arguments that could come into place. First of all, is it possible to have a chest size that's negative? Probably not. Right? That would be really weird. Even 0 would be weird. Okay? So I want you to notice that sometimes you'll see on videos online, they say, if there is no lower one and you want a negative number and really, really big, I can't even read these things on here. There it is. Above the comma is the EE button. If I do -1, e net to the 99, that would be -1 times 10 to the 99, which will be a huge negative number. If I figure this out, and I don't know if you noticed that the first time you came to this, you might have had that in there as the start, and I push paste, I get 15.8% or 15.9%. Really, really close. I'm going to go and do it again with 0. I wish I would have kept my decimal places. Maybe it'll still be there. Paste. Yeah, it'll still be there. Enter. What difference did it make? None. I'm going to do it again. I'm not going to go down as far. Okay? 71 definitely probably wouldn't be far enough. But let's go to 50. There, we got a difference. We got a difference when we went to 1, 2, 3, 4, 5, 6, 7, 8, then 9 decimal place. It had a difference. Okay? So when you're doing something forever lower, okay, the probabilities get so small. Technically, this bell curve has an asymptote at 0, and values continue off to infinity as a possibility, which in this real life situation we know for sure isn't true. Okay? But how tall is impossible? Like the tallest person ever was, does anyone like have that Guinness Book of World Records? You remember these statistics? It's tall, right? Is it like almost 9 feet or something crazy? Or is it almost 8 feet? I think there's been some on 8 foot something. You're looking it up? Tallest person ever? Do it. We need to know. 6'3". 8'11", almost 9 feet. So does that mean 9 feet is impossible? Or do you think someone will break that 9 foot? 8'11". Dad, would you hit your head on this roof? No? Is this 10-foot roof? 7-foot door? Huh? It would suck if you hit the projector when you came in. It sucked for me because I'd always have to readjust. So. But it's hard to say what's possible and what's not, right? I'm pretty sure that there will never be a 20-foot human. You never know, right? Okay. So when we go in a normal distribution, and on this one, when we figured it out, approximately, it became 15.9. With that -1 e to the 99, would technically include all of the values, supposedly off to negative infinity. But as soon as you go 5 standard deviations above and below, it's already so rare that its probability is basically 0, anything above 5 standard deviations. So if we look at chest sizes, and we have, you know, 95 centimeters, just happen to have, yes, I did steal these from IKEA, but I asked first. So there's our average, 95. With my sweater, I'm above average at this moment, okay? 5 standard deviations above would be at 5 times 8, 40 above 95, 135. 135, right? I would be impressive. You would do your homework. Right? You can imagine that? Very, very unlikely. 5 standard deviations below, take off 40, 45. See if there would be anyone. All right, you would not do your homework. You would just, wow. That would be extremely small. So 5 standard like the 5 standard deviations above, you can kind of like, oh, maybe, right? It's hard to, but when we go 5 standard deviations below, we're like, yes. There's very few 18-year-olds that I think that would fit into that, right? And how embarrassing would it be? You're 18, you're having to shop at like Gymboree and Once Upon a Child. Get that little onesie that fits you just nice to go to school. All right, sorry. Let's do the last one before I get too. Take out our crayon again. Above 87, if we it looks so much like a crayon, your brain can actually smell wax when you're doing it. You get that sensation. What would I estimate here if I used the 68, 95, 99.7 rule? Can you see that since I already figured this out to be 16%, it would make sense that the other half would be 84%. If we did this on our calculator and did the normal CDF, your lower one would be 87. Your upper one, you could do the 1e to the 99, would now be a positive with 95 and 8. You would get 84.1%. Before calculators, I wonder if I still have one. Before calculators, what should I do? No. I'll find one. Don't see it. Used to be formula sheets that they would give out. And you would get a huge chart of numbers to figure out every single percentage that was possible on your bell curve. So you'd be like, you would first have to figure out, they would say -1. So the first thing you'd have to figure out is, where's 87? 87 is one standard deviation below. So then you would find -1, and under the chart it would have 0.159. And you'd be like, okay, I know up to 0.159 is 15.9. Up to one standard deviation below is 15.9%. But now that we have our calculators, we can figure it out quick. The weights of bars of chocolate. Whoa, these are nice chocolate bars. 232 grams. And a standard deviation of 3.6 grams. Find the proportion of bars that can be expected to weigh less than 233.91. So again, we're going to want to, sorry, I have to apologize, that was a bad coloring day. That crayon work is not up to par. But we could draw our normal distribution, put our mean in the middle, add 3 standard deviations above. This time I just marked 3 standard deviations below. And I put a bar about where 233.91 was. Unlike what we had before, this one doesn't work out perfectly. But can you see that the percentage should be more than 50%? Because it's more than half. So we can go to our calculator, do our normal CDF, and get the value that would be roughly 70%. So 70% chance that you would get one less than 233.91. So how do companies use this? They know that when they make a chocolate bar that says 100 grams, that it's not going to be exactly 100 grams. There's too many things that could go partially wrong. They also don't want the variance or the standard deviation to be too big. People complain when they don't get what they expect. If it says 100 grams, what are you expecting? Something around 100 grams. You don't want to open it up and be like, what? Only one piece? That happened to me once, bag of chips. Most disappointing. You know, bag of chips, when they're full, they've got the air, so they look the same. They all look the same. I bought it at a canteen. I got my bag of chips. I opened up. one chip. Like, you would be mad. I was mad. This is not your. But if it was close to the right amount, and it wasn't like one heavy chip, it was like, this is the 55-gram chip. No, it was just one single, regular, light chip. Super disappointing. So, as a manufacturer, you want things to be relatively the same. As a manufacturer, if you sold a 100-gram chocolate bar, do you think people would complain if it was 105 grams? No, they probably don't. Now you're gonna like bring your own little scale before you buy your Kit Kats. You're gonna weigh them all separately and get that heaviest Kit Kat possible, because they're gonna weigh slightly different. So probably what they do is they try to make that their average is slightly above what they put on there, and that their standard deviation is low, so most of them are relatively small, right? Or maybe they're trying to skimp you and they all make their average just a little bit less. Probably there are even laws out there saying that your average has to be at or above, and your standard deviation can only be so much. Otherwise, consumers, it's not fair. Right? I see that when you go fill up for gas, they'll have a thing on there that the volume is measured at a certain temperature, at a certain, so they can't cheat you out of how much gas you get. And you can't get better gas or worse gas from somewhere else. All right. Babies. At a certain hospital, the babies weigh 3.6 kilograms. Is that heavy? Probably you guys know baby weights in pounds better. 3.6 kilograms times 2.2, averaging 7.92 pounds. Big babies or little babies or average babies? Do you remember how heavy you were? You were little?
No, but 7 pounds is optimal.
7 pounds? Well, that's pretty close, right? If we were looking at this, 3.6 kilograms, 7 pounds would be 3.2. So you are just one standard deviation, according to this hospital, below what is expected. And being between 1 and -1 is a lot of people. 68% of people would be within that range. Okay? We draw our little bell curve. Draw our line. Right? Was anybody here a super, super big baby? Yeah?
I don't remember how much I was.
35 pounds? No, just kidding. You don't remember exactly, but you just remember.
But my mom she's told me all of my life we're big ass baby.
All of you, or just the ass?
Sorry.
Oh, have you ever seen? Okay. Because you said you were. I have to put on. I had the first part on there. Because you said you were a big ass baby. And I asked if all of you were just the ass part. Which. Okay. Here's our answer. We're good. I am going to, let's take a little comedy break.